Ciao friends and welcome to a new video from SQL BI. In this video, we are not going to write DAX code together as we often do. Rather, I want to check with you the performance of different versions of the same measure. The measure is rather simple. It just checks whether a product has sales or not in the given filter context. And this might be useful, for example, to find which products are not sold in a specific year, in a specific area, or whatever. As it often happens with DAX, you can write the same measure using different functions, different techniques. And it is always important before going in production to test several different versions of the same code, searching for the best one, so that you are sure that you are using the resources of your instance in the best way. So let's start together first by looking at the different versions of the code, and then we measure performance, we reason on top of it, and finally we make our choice. Let's get started. As I said, the measure we want to compute checks whether a product has sales or not. So the measure is named has no sales, and I have different versions in the same query here. We have the first measure that just checks whether the sales amount is equal to 0. The idea is that a product has no sales, of course, if the sales amount is 0. Then we have a different version that makes the assumption that if a product has no sales, then there will be no rows in the sales table. So rather than computing the sales amount, we just count the number of rows in sales by using count rows. Then we have a third version that instead of using count rows equal to 0, uses the isEmpty function. The hope is that isEmpty is going to be faster because it's a special function dedicated to check the emptiness of a table. But then we have other three different versions that are a bit more intricate, but maybe they produce a better performance. One is to use a set function, intersect, so we check whether the values of the product key and the values of sales product key have any intersection. If there is no intersection, means that the product has no sales. So if the intersection is empty, it means that there are no sales. Intersect is going to be solved by the formula engine, but maybe performance will be good. Then we have another version that instead of using intersect uses except. Maybe, again, except is faster than intercept. We don't know, we need to test it. And finally, there is the last measure that is probably a bit more intuitive because it assumes that if a product has no sales, first there are no rows in sales, and we use the measure placing the product name on the rows of the matrix. So we check if the selected value of product key belongs to the values of sales product key. So if the currently selected product belongs to the currently being sold products. Which one of these measures is faster? That is open to investigation. So the entire video is all about testing performance, measuring numbers, and finally making the decision. Let's start with the first one, that is has no sales count rows. I'm using this query that summarizes by year, month number, product name, and then checks has no sales. We just use the right measure here. The first measure we use is has no sales, sales amount. Let me just check the name. Is has no sales, sales amount. I just need to check that the query plan and the server timings are enabled. Then we minimize it so we have a bit more real estate, and we run the query. We get the result, and here it is. It takes 700 milliseconds, around 2 seconds to run. I usually run the query at least twice because maybe there's something in the cache. 2-3 times just to check that the numbers are right. You see, this is definitely too large. 3 seconds is probably an outlier. 2.6 seconds looks like a good number. So the total execution time is 700 milliseconds, 2.6 seconds in the storage engine CPU. Remember, it's always important to look at the storage engine CPU, not just at the storage engine, because the storage engine is only 340 milliseconds, but that is due to parallelism, and we want to measure how heavy a measure is. Let's take a look at the algorithm. We have a first query that gathers the product names, and that is needed because we are grouping by product name. Then we have a second query that gathers the year and the month number. Again, that is needed because we are grouping by year and month number. And finally, the last query is exactly what we would expect. In XMSQL, we have a query that computes the expression of the sales amount and then groups by year, month number, product name, and computes the sum of expression. This is the query that uses most, if not all, the storage engine CPU time. It produces around 300,000 rows. And after we have finished doing our work, so after the code has been completely executed, we still have 362 milliseconds of Formula Engine CPU. Here it is. The amount of Formula Engine CPU is quite large, so the algorithm that the engine is choosing is quite clear. It is computing product by product, scanning sales, the sales amount, but then, because we are interested in the rows where the sales amount is equal to 0, it needs to gather also all the product name, join the two results in order to retrieve only the product names that do not have a sales amount. We don't want to go deeper in the algorithm, but it's important that we use Ctrl F9 to store the result that we have found so far. So this is no sales using sales amount. 700 milliseconds of storage engine of total execution time, 362 is the Formula Engine, 340 storage engine. The most relevant number is 2672, that is the storage engine CPU. That is probably the easiest measure, the one that comes to the mind to any developer. But if we can make the assumption that a product with no sales will have no rows in sales, and that assumption is valid in case you are just storing sales inside the sales table. If you are storing sales with quantity equal to 0 to store items which are returned to your shop, then this technique is not going to work. But maybe the idea is that by just counting the number of rows in sales, we avoid this calculation. That is the multiplication of quantity times net price that uses two columns in the fact table. So we just need to just count rows. We go in our query, and instead of has no sales amount, we execute has no sales count rows. We run it. That's 1.3 seconds. We always run through 3 times just to get a number that looks better like the average, but 1.3 seconds looks like a constant value, a good result. No, that goes to 2.5 seconds. Let's run it again, 1.8. Let's use 1.8 because as you see, the variation of number is quite large. So we need to find a good average. 1.8, and let's take a look at the algorithm. We have a first query that still gathers the product name, a second query that, exactly as it did before, gathers the year and the month number, and the third query retrieves the same number of rows, but this time it's just computing year, month number, product name, and then the count, the number of rows. This query is simpler than the previous one. Indeed, you see, it takes 1.8 seconds of storage engine CPU rather than the 2.6 seconds that it was using earlier. The difference is quite important because it does not need to scan neither quantity nor net price, so it's going to be faster. And so far, it is our best choice. As we did before, we just save with Ctrl F9 the numbers, and this is no sales with count rows. Now, if we look closer to the query being executed, you see that it gathers the year, the month number, the product name, and then the number of rows, because we need the number of rows to perform this condition, that is, count rows of sales for the given combination equals to 0. Maybe, using isEmpty, we have a better query plan. isEmpty doesn't really need to count the number of rows which are present for any combination. It just needs to check whether the combination exists or not in the fact table, because isEmpty returns true only if the combination is not present at all inside the fact table. So our hope is that this version of the query is going to be a bit simpler. Let's give it a try. We have has no sales is empty, and as usual we execute it a few times. See, the execution is faster. Now it's only 1 second. We run it again, 1.4 seconds, and then again it's 1.4 seconds. So we stick to 1.4 seconds as our timing. Let's take a look at the queries being executed. We have again a query to gather the product name and a query to gather the year and the month number, but their duration is so small that they are totally irrelevant. Whereas at the storage engine level, the last storage engine query gathers by year, month number, product name, and it doesn't even compute the count. It just retrieves the combination of year, month number, and product name from sales. Therefore, we expect the query plan to be simpler. It is not really much faster than the previous one, even if it is faster, but not that much. Let's store the numbers. So we have 593 milliseconds, 363 milliseconds of formula engine, 230 milliseconds of storage engine, including parallelism, and 1.4 seconds of storage engine CPU. This is no sales using isEmpty. And again, so far, this is our best choice, because 1.4 seconds against 2.6 seconds is a lot of time. It's 1.2 seconds out of 2.6, so it's really a very good improvement. The last three versions that we want to check, they are a bit more intricate in terms of algorithm, because we gather for has no sales intersect the values of product key. These values only needs to scan the dimension, and product being a small dimension, I wouldn't expect this to take a lot of time. And values of sales product key, that requires to retrieve the distinct all the possible values of the product key gathered from the fact table. This might produce a level of materialization that is larger than the 300,000 rows that we see here. And then we check if the intersection between the two sets is empty or not. We already use isEmpty. There is no need to check for count rows equal to 0, because we already know isEmpty is going to perform better. So we use intersect here, and we use it here again, and we run the query again. 2.4 seconds. It's actually worse than before. Let's run it again. 2.4, 2.8, and then again 2.4. So we stick to 2.4 seconds. You see that the number of storage engine query is increased now. We have the first one that gathers the product name, the second one the year month number. The third one is interesting because it retrieves the relationship between product keys and product names. Why that? Well, if you look at our query, we are grouping by product name using summarized columns. But then from inside the measure we reference product key. So the engine needs to have the relationship between product names and product keys in order to produce the final result. And the last query that generates the same number of rows which has been generated before, and it gathers the year, the month number, the product name, and the product key. Both product name and product key are present. So it gathers all the possible combinations of year, month number, product name, and product key. And then, as it happened before, because we are interested in removing values, it will need to perform the intersection inside the formula engine. Indeed, you see that the amount of formula engine CPU is slightly increased. Now it's 467 milliseconds. But as we did before, let's save everything. It's 2.4 seconds, and this is no sales intersect. It's interesting to start looking at these numbers because at 2.4 seconds, that is already faster than the naive solution, the one using sales amount. But the formula engine is a bit slower, and so far is the worst performing from the formula engine. From the formula engine point of view. We have it here. 467 against 362, 4963. So the version with intersect is the worst one because it's using intersect that requires the heavy intervention of intersect. We have another version using except. This actually uses the very same algorithm we have seen for intersect, but it's using except rather than intercept. I would expect the two versions to provide exactly the same speed, but we are here to test it. So we place it there, we run the query, and let's see the numbers. 2.4 seconds, let's run it again. 2.6 seconds, a third time just to make sure, and 2.9 seconds. I'll go for 2.6 seconds. Let's hope we have something around 2.6. No, 2.9 is the number we have. This version is, well, we need to check it, but I would expect it to be very, very close to the one with intersect. The first query gathers the product name, then the year month number, then the product key and product name, and finally in the last query we gather all the combination of year month number, product name, product key. So apart from using a different function, sales_except is basically the same as sales intersect. Let's save the numbers. You actually see it's slower, but probably there is something in the query plan that makes it slower, because everything else looks close to the other ones. Anyway, is way worse than our best choice, that is so far the version with is empty. So this is no sales except. The last version looks promising because the last version assumes that you are slicing by one product only, and it's using the in operator to check whether the selected value of the product key column, provided that you place in a matrix the product name, there will be only one product key selected, therefore selected value returns the currently selected product, and you just check that that product belongs to the ones that are currently being sold. So this might be our best option or not, I don't know. Until we measure, we actually don't know. Let's run it. And oh, that is definitely really, really bad. 43,000. Let me run again, just check that there were no particular issues. No, it's 40,000. So let me just save the numbers as a first step. And then we look at the query plan. The query plan contains first gathering the product name, then the year and month number, as it happened before. These are required by summarized columns. Then we have this kind of strange query that is very common when you use selected value. It gathers the product name, checks whether the value is blank or not, and then the minimum and maximum product key by product name. The result of this query is needed to check whether by product name you will have or not only one product key. So it makes it easier to check whether selected value needs to return a blank or not given a product name. Remember, we are grouping by product name here. And then the last query, the one that takes forever, takes 40 seconds of storage engine CPU, which then, due to parallelism, are reduced to less than 1 second, but still it is using 40 seconds, is really, really bad, because being bold, I would expect it to contain a callback. Indeed, we have our usual grouping by year, month, number, product name, the join, but in the where condition, we have a callback DTD for the values of sales product key. Now, the presence of a callback kills performance because it requires the storage engine to constantly call the formula engine. And if that happens for many, many times, of course, performance are going to suffer. I think I have already saved the numbers here, so let's just write no sales selected value. And we can now draw some conclusion. If we were to make a choice between the different versions, which would be our winner? Well, this is pretty clear. The version with is empty, because it's constantly faster than all the other queries. It's better from the storage engine point of view, from the formula engine point of view. It's not the best, but overall is definitely the best. And from the point of view of the storage engine, it actually uses a lot less CPU. So this small increase in the formula engine actually is compensated by the gain that you have in the storage engine, because the query is actually faster. It does not need to count, it does not need to compute the sales amount, it just needs to check whether there is a specific combination in the fact table or not. As you have seen, by measuring performance of different versions of the same code, you are able to make an educated choice. Whenever you write code and you know this code is going to go in production on a large model, or if you care about performance at all, being able to measure the performance of your query, write your query in different ways is absolutely important. Because first, it gives you some insights about how DAX solves your query, and the more you know, the better your DAX code will be. Second, you save a lot of money because it made the case that your model will work on a smaller instance of Power BI because it uses less CPU. And then it gives you the confidence that the code you are running is optimal. It's a lot of fun to optimize DAX. It requires a bit of time in order to learn the basics and to learn how to use the tool, but then it's absolutely amazing. Enjoy DAX!